everyone, welcome to another video of mine. In this video, I want to talk about nested learning. I think this is probably the most important paper in machine learning in 2025, since it solved one of the biggest problems with LLM, and I think it has a very creative way of thinking. I will talk about why it's important and then go to how they solve this problem. So, in this paper, they start with talking about human brain and the analogy that LLMs are like a amnesian person. Basically, the problem with LLMs is that they don't have a connection between their short memory and a long-term memory. Imagine an old person that lost their memory and they wake up every day, and every day they think it's Monday, and their wife is still alive and they want to go to work and everything, while it happens every day and they don't restore new memories, but they can remember stuff from 20 years ago or when their wife was alive. Basically, same thing is happening with LLMs. When we have input, it will learn the context, but it cannot store it in the long-term memory. That's why when you are chatting with some of these LLMs, there is a limitation for how long you can chat, because basically what the LLM does is having this black box, and you tell it tell LLM to do something, and it generates some text and store it somewhere. And when you ask a new thing, it will pass whatever was its answer plus whatever was your prompt all together to the LLM, which can lead to various problems from forgetting or higher hallucination and so on. But our brain doesn't have such problem. The question is why? To answer this question, it's good to talk about how actually our brain works. I will talk about some basic stuff. Of course, I'm not a neuroscientist, so it will be pretty basic. If you know everything about the brain, you can skip this part. How our brain works is very layer by layer. The lowest layer of memory is in the neural level. There is a famous quote in neuroscience say, neurons fire together, wire together. Imagine this is my presynaptic neuron, like A, and this is my postsynaptic neuron, B. Oh, and if you don't know what is a neuron, basically neuron is a cell that make our brain. It's the smallest computational unit. And the synapse is just what connect two of these computational units together. There is a guy named Pavlov, and he did an experiment. I will talk about his experiment and come back to this neurons fire together, wire together. He did was having a bell. Imagine this is a bell. I'm not good at drawing. And a food for a dog. And this is the food. And this is the dog. He used to ring a bell whenever wanted to give the food to the dog. And what dog learned was when it heard the ringing of the bell, it start to have saliva. So basically, he associate these two uh, events together. On a neural level, this thing happens with a very simple rule of learning, which calls Hebbian learning. Our neurons are oscillating randomly during time. Why? Because there is a Brownian motion of ions inside each of these neurons, and sometimes some of them reach a certain level, certain threshold that start firing. So even now that you are watching this video, there are so many random neurons that are firing inside your brain. And when Pavlov was giving the food to his dog, some of these neurons were firing randomly. Imagine a neuron like A was firing and sent some message to neuron B. It was completely random, and it happened all around the dog's brain. The next time, it happens again between so many neurons, but some of the random neurons that was chosen or was randomly firing in the first time were similarly firing in the second time. This thing make the synapse more strong. So whenever neuron A fires, neuron B fires much easier. What does that mean? Because it's a bit probabilistic. Not always a message can pass through a synapse, but when it start to fire together more and more, it start to wire together more and more, and the uh, message passing process will be much more easier. I said all of this to say that this is the lowest level of memory. We have several levels of memory in our brain. First thing is that you have a context memory, which is something like I tell you a number and you read it to put a pin inside your phone or something, and after that it will be gone. There is another memory which is short-term memory. You remember some stuff about today, but if I ask you about it next week or in a month, you will not remember. And there are some stuff that is in your long-term memory. And if I ask you even years later, you will remember them. But how brains have these layers and pass the information through these levels? How it works is that basically while we are sleeping, brain uploading these memories through different parts. The memories that stored in the prefrontal cortex will process in the hippocampus and then sent to a neocortex. And it's done via different uh, wavelength during these processes. Basically, we can say hippocampus is a gateway for encoding new memories. And in this paper, with the help of nested learning, we are trying to have this online process of memorization and have the information that the LLM or our machine learning model learns in the long term. They have a very good quote in their paper which basically says memory is a process of neural adaptation, and learning is a process of acquiring efficient and useful memories. I think this is the one sentence summarization of this paper. Basically, we don't need just memorization, but we need the real learning in this process. If we want to write it mathematically as they explain in the paper, M, which is the process of memorization, is minimizing loss or an objective like M for keys and values for each input. So basically what it's saying is that we are trying to minimize the difference between what our model already knows about the V over a function like M. So basically memorization is a mapping of the data into some objective, with some objective. And this formulation is similar between sequential modeling, like the model that we are already using, like transformers and so on, and the nested learning. So basically, if we go to the next figure, here you can see that our memory will go through the model through a gradient descent, which just will happen during the training, which this backpropagation will optimize the weights of our model, which is basically equal to the memorization function that we wanted. So if you want to write this down, we can formulate it as the weights that will be changed is equal to minimizing some loss function over the current weights and the data that we have for training. In such model, we can say that our ut1 equal to the function that we had for our loss over the weights and a data point. And we can interpret it as a local surprise signal, or LSS, and that represents a specific quantification that specifies the mismatch between the current output and the objective that we have for that input. And furthermore, for our nested learning model, we replace the gradient with a momentum-based variant. Instead, they use the gradient descent with momentum in the nested learning instead of a gradient descent, and this has a two-level memory. One level is the memorization of momentum, and one is the gradient descent itself. So basically, it's very similar to how our brains works. And we can see it as a two-level optimization. In one level, we need to optimize the momentum, and in the other one, we need to optimize the gradient descent. They also talk about similarly multi-level optimization for transformer architecture and multi-level architectures, but I will not go through them. I think the MLP will give you an insight that we can see the optimization of MLP as either one-level optimization or two-level optimization. Even with the momentum gradient descent and other tricks in different architecture, which we have different layers of memory, we still are not sure how we can use these levels of memory. That's why we need the nested learning. Here we can define a frequency for our model. Frequency can be defined for any architecture from attention block or so on, which are a non-parametric components, and also for the parametric components of our architecture, such as learnable weights or momentum term in the gradient descent with momentum, or so on. Frequency basically defines that number of updates that we have over time. And then we can update our model with gradient descent, but each level of model, which means each frequency will be updated by its own speed. So for example, in this shape that you can see here, we have level 1, which have f1, and level 2 with f2, and level 3 which is the f3. Basically what is difference between them is the number of parameters that we are updating during time. You can think about it as short-term memory and the long-term memory in the brain. And each of these levels will have their own special updating, and they call this in associated system a neural learning model. And this can let us to learn parameters with different levels of abstraction with different time scales. Also, they have another creative idea, and this one is thinking about the gradient descent with momentum. Here we have the weights in the next step, and the momentum as a learning module. And basically, they introduced the Adam-like optimization for the momentum and try to express it as a valueless memory. However, as you can imagine, it's a pretty limited sort of memory. And you can think about it as a meta memory that inside it has the memory of past uh, gradient steps. Another technique that they had here to make it even more uh, more comprehensive is using a nonlinear function for the momentum. So basically, as we had previously, the weight like this, they put a nonlinear function here, and they argue this technique can increase the power of the momentum memory to add this nonlinear function before it. Here they use the Newton Schultz function, but of course it can be any nonlinear function, and it will increase the power of our memory. Now let's talk about hope, which is one of the main features of their architecture. But before, let's talk about the existing architectures. The existing architectures has two parts. Architectures like transformer has a part which is the attention mechanism, and a part for the feed forward network. The attention mechanism basically represents the combination of the information across different sequences, and the feed forward basically uh, acts like a presentation of knowledge storage during the pre-training phase. And based on the things that they learned from brain, they suggest that the architecture can have two parts, and instead of feed forward they used something uh, known as knowledge storage feed forward, which is similar to the feed forward layer or network, but instead it occurs in every layer of our hope architecture. Another thing is a self-referential learning module. Maybe I can go to the next figure in the paper and explain it there. Which basically means self-modifying Titan means an architecture that learns to change itself. So basically, firstly, evaluate how different is its output with the answer, and then try to change itself. Basically, with these different frequencies, go and change different levels of itself. And here you can see how it can make the difference. Basically, it will replace the attention head itself. With this, I will finish the explanation about hope, nested learning, and this whole new architecture, and try to talk about the result. As you can see, nested learning with hope was basically the best during so many different benchmarks. I think the most important benchmark is the IRC, E and IRCC. As you can see, it improved both slightly, um, especially with lower amount of parameters, and for more knowledge base and uh, less reasoning, less abstract one, it increased less. So if I want to conclude in a sentence, I would say hope is very good if you have limited amount of resources, if you want to have online learning, and if you want to have a better abstraction and multi-level abstraction. All in all, I think we will see much more architecture based on hope, and I hope you enjoyed the video. If anything was not clear, you can put it in a comment. If there is a paper that you like to know more about it, or if you like to have an implementation of this paper, you can just drop a comment. If you like the video, please press the like button, subscribe, and share with your friends. Thank you so much and have a nice day.